If you could, Mike, if you could let people in, because there's no way I got to do both things at the same time.
Yep.
All right, so what are we going to do today? I strongly suspect this is going to be the first of multiple ROS2 PX4 talks, just based on what's happened. Um, I posted a LinkedIn message to say that we were going to do this session, and it had 60,000 impressions on LinkedIn, which is more than the impressions we got for the last 2 years. So obviously there's definite interest here. So the agenda is we're going to talk about news. We're going to talk a little bit about what is PX4 and ROS2 because I really don't know. I'm a PX4 person, so I don't know if people are coming from ROS2 or coming from PX4. So we're just gonna, hit the high points. And then we have a demo. The demo that I'm doing is basically taken from the documentation, which is a custom flight mode. So tracing the letter R for in QGC. So we can see it in Q ground control, and then it's PX4. And then I will talk about somebody did a really good demo, which is object detection using YOLOv8 in a PX4 simulator with Gazebo. So I'll just talk a little bit about that. But I suspect I'm not going to have a huge amount of time. And then we'll just, a couple of things about where you can find all this. But we always put the code up online. So if you want to start playing with the code, it's pretty straightforward. Hey, was ever talking? Can you mute if you don't mind, please? So in the last month, we had 465 new members, which is 40% new membership in a month, which is amazing. I've been doing this for 2 years, so this is definitely taken off in a way that I didn't expect. Hey, Mike, can you fix that? I don't know who's talking.
Yeah, I did it.
Thank you, sir. Okay, and so this month we're going to do PX4 and ROS2, and then next month I suspect we'll do a few more PX4 and ROS2 talks. And the next month, I had a few people ask me about building a custom remote controller. Remote controllers, can be really expensive. They can be, 5 grand for an RC. So basically, what we did is ordered a bunch of things off AliExpress, and then we're just, using 3D printing to print our own RC. So that will be next month. That will be April's talk. You'll get the bill of materials, and you'll get the what you have to do in order to get everything going. So if you want to get into some low level electronics, it's basically it's the same as putting together a drone, really, as far as I'm concerned. So I'm looking forward to that. That should be fun. And then probably the month after that, we will do um, another ROS2 one, maybe something a little more difficult than what we're doing tonight. Okay, so what is PX4? So this is the people coming from the ROS2 side. So basically what it is flight controller software. So the drones, that the thing that drives your hardware to make the drone fly. It's open source project, a lot of configurability. So you get the firmware, the tools and integration for kind of the software in the loop simulations, hardware in the loop simulations. It's kind of hardware agnostic, so it can be used on lots of different flight controllers. So, the classic Orange Pilot, the Orange Cube, and then we have Pixar, Calibro, NXP. So there's quite a few out there that support the specification and they can run PX4 software. And then it communicates with ground control stations. The thing that everybody typically uses is Q ground control for telemetry and mission planning. And then it communicates using the Mavlink protocol. You don't have to use Q ground control. We've written our own GCS as ground control stations using Mav SDK, so there's no reason why you can't do that. And it's RTOS based, so it's runs on NUTX real-time operating system. And then it's very similar to ArduPilot, but sometimes that can get confusing, especially for people who are just into this. So there are really two branches, two big code bases. One is PX4 and one is ArduPilot. The main difference being in the licensing. So ArduPilot uses a strong copyleft licensing. So if you do anything in ArduPilot, you basically have to give away the source code as far as I know. Correct me if I'm wrong. And then PX4 uses a more permissive license, which kind of it makes it much more common in use for, commercial companies. Okay, and you could literally talk about that last point for the rest of the meetup, but we won't do that. So what is ROS2? So ROS2, ROS stands for Robotics Operating System. So it's basically, it's not essentially an operating system. It's a bunch of packages. So it's an open source ecosystem of packages. For ROS2 is much more decentralized than ROS1, which was basically a centralized model. So ROS2 uses DDS for decentralized communication, so makes it much more robust and allows us to start doing things like connecting to PX4, and then we can connect to all the wonderful nodes that we have in ROS2. So that's why I think that there's a lot of interest in this at the moment. So it's a multi-platform framework for managing communications to all parts of your system. So each of the systems are represented as nodes. We got a publish subscribe model between the nodes, and then the first example that we're doing is in C++, but you can also do in Python. The second example is Python that I borrowed from out there on the internet. So nodes are the smallest units of your system, so they should be responsible for a singular modular purpose. So that could be publishing data from a sensor. Sensor could be a camera, could be LiDAR, could be anything basically. So nodes can publish or subscribe to topics. And then in here we have just a message that's coming from one node and being, it's because it's been subscribed to other things. So in a drone perspective, what we would do is we could do telemetry, we could do cameras, we could do movement, all sorts of different things. Okay, so ways to extend PX4. So a lot of times up till when this kind of integration started happening between ROS2 and PX4, a lot of what was happening was that people would just rewrite the firmware in PX4 to make it do different things. They would bolt on a computer and then use the Mavlink protocol to basically uh, pass information back to PX4 so that PX4 could do something with it. But what seems to be the way that everything is going at the moment is that we're looking at using off-board control using ROS2, and that seems to be really accelerating in interest. So like I said, kind of the history has been up till now is that you're basically using Mavlink commands for setting position and whatever altitude targets. But as the tasks get more and more complicated, ROS2 kind of allows us a really neat way of being able to write better code so that we can write whatever functionality we want. In this case, we're going to get it to do a weird custom pattern for the letter R, and basically that's sitting on a node, and it's much more extendable if we want to change it to something else. If we want to do something that PX4 doesn't do out of the box, ROS2 allows us to do that in a way that is much more elegant than trying to hack through the PX firmware. Okay, so ROS2 can read write to PX4's internal interprocess communication API. So anything controlled by the API is fair game. So what we're using is an Auterion package, which is PX4 ROS2 interface. So that enables us to do things like creating custom flight modes, creating flight mode executors. So they're sequence state machines of flight modes, and that's really how we're doing our custom flight mode tonight. And then overriding existing flight modes with new behavior. So for example, the lawnmower pattern, because you see something that you want it to go, you could basically override the behavior without destroying what the current path is. And then it can also, like waypoints, it can use set points, so we can control the drone movements via set points, which would be position, velocity, altitude targets for the drone. And then we can also integrate with other ROS packages. So one of the things that we're looking at in the second example would be, using object detection. So YOLOv8, there's a lot of work that's happened on the robotics side of the house, and because of this interface, because of the Auterion library, that allows us to get access to all the cool things that people have been doing on the, for warehousing, et cetera, on the ROS side of the house. And then we can also use some of that code within our drone applications. Okay, so what do we need to get started? So somebody asked this earlier on. So we need recommended that you start off with Ubuntu 2204. I did put the user guide in the resources, so a lot of what I have, anything that I'm talking about today. So tomorrow I'll put up the slides and I'll put out a link onto the meetup group. The video should be on YouTube, so if you want to look at this afterwards. I love when people ask questions on the meetup group, so if you have anything that you want me to follow up on, please do, because we're always looking for topics that people are interested in. And the resources will basically have a list of the 3 or 4 major websites that you should go to, and we'll look at them at the end too as well. So the PX4 documentation for ROS2 is, I'm basically stealing a lot from that, so you can go there and find the same information. So we need to start off in Ubuntu 2204. I'm on a Windows box a lot of the time, so WSL works great. So if you're on Windows, you can do that. Somebody asked the question earlier on about can you use Macs, and Auterion, who did the package that we just mentioned, are all on Mac, so that should be okay too. If I was going to recommend anything, I would just run on a bare metal Ubuntu box. A PX4 toolchain, so we can find out where we need to do to get that. If you're not used to that before, we're going to use ROS2, we're going to use the humble version. And then we need this micro XRCE-DDS agent, which is the bridge for getting the two to talk to each other. Okay, so if you, in a terminal, basically, if you want to install PX4, this is the classic way that you would do it. So you git clone it. We'll also have to do the same with a few other things, but with this, run the Ubuntu command to make sure that everything's installed, and then you cd into the directory, and then to get the simulator to work, you do make PX4 SITL. So the docs on the px4.io have everything you need to install ROS2. You can go through the humble documentation, but it's much quicker to do it if you just go to the PX4 and just cut and paste what we have here. So in another terminal, in order to install this ROS2, you basically just run all these commands. And then the last thing that we talked about is that we need to have our bridge. So the first step in extending PX4 ROS2 is to enable communication. So but what we really need is for PX4 to be able to subscribe to some of the topics. So PX4, maybe it wants the GPS position from ROS. So I need to be able to publish that. I want the PX4 topic for GPS position from ROS. So how can I publish to a topic for position targets? So PX4 and ROS2 use completely different communication messaging systems. So PX4 uses micro-orb, so that's the micro object request broker, while ROS2 expects nodes to communicate using ROS messaging. So we need a bridge to translate between the two, and that is the micro XRCE-DDS agent. We basically have to git clone that. I'll show you how that works. And then the client is built into PX4 firmware, and then the agent runs on a companion computer. So the commands to get that to run are git clone, the micro XRCE agent, build it, make it, and then you basically have to link it to your user local lib library. All right, so then now that we have our bridge, so what do we have so far? So we've installed PX4, we've installed ROS2 Humble, we have our bridge, and then we want to create a workspace for what we're trying to do. So just create whatever you want to call your workspace. I'm just following what it said in the documentation. We're just going to call it my workspace. We are going to copy the PX4 messages repo. I will say that's the first thing that you might fall into trouble with. So you want to make sure that whatever the version of the PX4 messages is the same version, the same minor version that you're using in the version of PX4. The version of this repo and your PX4 firmware need to be the same. So when creating your own custom code, you'll add it here just like any other package. We go back into the parent directory, we source the ROS commands environment variables, and we build the project with the ROS build tool, which is called callcon. So if everything goes well, you're going to end up with your workspace with a tree that looks something like this. Okay, install contains setup files for environment, build contains whatever build artifacts, and then we have our log files. Okay, so in a terminal, we want to run the following from the top level of your workspace. We want to source the setup for our ROS Humble. We want to load the project's environment, and then we don't have anything in our package yet, but we will do in a second. So basically, what you would do is you would say ROS2 run whatever the package name is and whatever the node name is. So let's go have a look at what our first example is. So our first example is creating a custom flight mode executor. So we create a custom flight mode executor for a drone, and it should perform the following when loaded. It's going to arm, it's going to take off, it's going to trace the letter R, and then it's going to return and land. So this example can be found I put it up in the resources, just under my GitHub. So it's github.com/GodfreyNolan. If you just look for it, you can find it there. And that's based off the example from Auterion, where we just changed a couple of things just to get it kind of up to date with the latest versions of PX4. So essentially what it's going to have is on the left-hand side, we're going to have this, you can see where all our flight modes are, so all the usual ones, and we're adding our own custom one at the end, which is to draw the letter R. And then when we run it in Q ground control, basically what it does is it follows the pattern of the letter R. We'll show how we get that. Now, this is something that if you were trying to do it in Q ground control, I don't even know. Well, I kind of know where I'd start, but it's not something that Q ground control, the way that I have found it in the past is it's basically it's JavaScript and C++. It's not, it seems to be a lot of effort to get the smallest thing done sometimes, especially if you've never done it before. So one of the things that I really like about ROS is because the code is compartmentalized into our little node, it makes the code that we're trying to write so much easier to understand and to get something going. So the picture on the left shows a local QGC build of, in this case, I think we are using version 4.4 branch. The custom flight mode is visible. If you do this with the Q ground control, just as you know, as an app image or whatever you're running it, it probably won't show the custom flight mode. So you will have to do an extra step here, which is to make sure that you're installing Q ground control locally. It's not to say that it won't work, but it just won't let you choose the flight mode. You're just going to see draw or here when you start everything. It's just basically going to take over the mode, the flight mode. Okay, so how do we do it? So I'm going to talk about the setup for everything that to get the actual code working. So this is more of the configuration of the environment that we're setting up. I'll show you what those different things are in a little video that I've done. Then I'm going to talk a little bit about the code. And when we go through the code, I'm just going to show how we wrote a little bit of C++ code to have the state machine that allows us to create the letter R. But we'll do that afterwards. So we're going to talk about the environment first, show a video about how to set up the environment, talk about the code, and show the end of the video, which shows the code working. So we're going to set up a new workspace, going to add our custom packages, we're going to set up the simulation environment, and then we're going to run our custom component. So our new workspace could be a ROS workspace. We're going to have our custom package. We're going to add that to the workspace. We're going to run everything we need to get the simulation environment working. So that's Gazebo, which is our simulation. Could be Jasmine as well if you wanted it, but we've just used a Gazebo. We're going to use our micro XRC agent, which is the bridge that we talked about, Q ground control, and then we're going to run a ROS package. And then if you're going to use QGC, you either have to have it installed or you have to have your local version running. I recommend a local version. Okay, so we're setting up a new workspace. So similar to what we did before. Make a new folder for the workspace, clone the dependencies. So the dependencies that I want my PX4 messages, which is what we mentioned earlier. And then we want the PX4 ROS2 interface. If you are using the 1.15 branch of PX4 messages, you need to make sure that you're checking out the PX4 toolchain, which is a compatible version, which would be PX4 version 1.15.x. We're going to clone the custom package, so I'm not going to talk about the code yet. I'm just going to assume that you just want to use the code that I wrote. So you git clone the slightly modified Auterion code that we have, which is basically going to pull that into our custom package. We are going to build the workspace and set up the shell to run the ROS commands later. So basically do the setup, install, do the build command for ROS, and then run the setup command. Okay, so for now, we'll just add the custom package like other dependencies, and then we'll dive into that a little bit later. We need to start our bridge. So we need to start our micro XRCE-DDS agent. And the command is setting it up in port 888. Okay, so next we want our simulator. So this is the Gazebo. So we are seeding into PX4 that we've already downloaded. Want to make sure that you have checked out the version 1.15.4 and then just do the git submodule init recursive because otherwise everything won't work. And then if you haven't run the bash command, run the bash command to get Ubuntu set up for PX4. And then you do make PX4 SITL Gazebo X500. Other versions of PX4 will probably work, but we tested on 1.15.4. Okay, and then if everything works, once you run the make PX4 SITL command, you should get to see Gazebo. Okay. And then finally, what we want to do is we want to launch Q ground control, and that it should connect to the simulator automatically. Unless something dramatic has happened. Okay. Because we've downloaded the code, we can basically run our draw flight mode to draw the letter R. So this is we're running a ROS node, so ROS2 run, and then we're basically calling our mode and asking it to draw or. So the drone should immediately switch to the custom flight mode and begin the procedure outlined earlier. If you have a local QGC, you should be able to see the custom flight mode appear in the dropdown, and then you can choose it there too as well. After running the command, QGC should indicate your flight mode has been selected. And the last version of QGC that we were using was 4.4. Be careful of the daily builds. So just make sure that you're using the last stable build and you shouldn't have any issues. Okay, so let me show you what the setup is first before I go into the code itself. Okay, so I have a screen share here. I just want to walk through. Let's make it a bit bigger just to show you what we're doing. So we're making our workspace, cloning the code, the messages, cloning the ROS2 interface. Okay, and then cloning the code. That was the modified version of the Auterion. Source the humble setup, do the build. Okay, so it takes a while. Okay, then we want to install. On a separate terminal, we want to run our micro XC agent, and you should see something like this when you're running it. Okay, now we're going to PX4 autopilot, and we are setting up our we're checking out version 1.15.4. Make sure that we have all the right things in there. And then we start our Gazebo simulator. I like to show the video of the code actually working because a lot of times just find stuff that doesn't work the way that it's supposed to be working. So hopefully the video hasn't stopped here. Okay, well, all that you're basically going to see there is the Q ground control. So I'm going to stop this right now, and then we can return to it in a second. So we were almost there. So what we were trying to get to was to get Gazebo running with Q ground control. So I didn't want to go too far because I wanted to show what the code is before we go any further. So now that we have our custom package, let me show you where everything lives. I can show that too as well. So here is where the code is. So everybody has access to this. This is a public repo, so it's under my name, Godfrey Nolan. PX4 ROS2 custom flight mode. So we have our main CCP, which is not really much happening in, and then we have our mode HPPP, which is our just include file, which a lot of the code is in. I might refactor this and actually move this over to the CPP at a later date. Okay. So let's talk through the code to give you a better idea about how it's put together. So basically what we're doing is we have a state machine that does a number of actions to draw the letter R. Okay, so here we have the package structure. So this is for any ROS2 packages built using CMake. So there's two languages you can use, C++ or we can use Python. So the main CPP file is small, just creates a ROS node from the custom flight mode executor and flight mode defined in the mode HPP and runs it. So all of the action for us for this project happens in mode HPP, which is the header file. Code is commented in more details, but we'll go over some parts. So we have the package structure. The next thing we want to talk about is creating our custom flight mode. So a custom flight mode should inherit from the base class, which is in the Auterion library. The constructor should, so basically what we have is we have draw flight mode. We have a constructor, a destructor. We have onActivate, so that's called when the flight mode is selected on the drone. And we have onDeactivate called when the flight mode is unselected. And then update set point is basically called repeatedly during the flight. And within that, we're going to tell the drone where to go. That's what's actually controlling the drone. Okay, so in our constructor, so we'll be using, this is example setup, go to set points using Auterion's PX4 API. This is the go-to set point that we're looking at here. So that allows you to set an end position, yaw, and max speed targets for the autopilot to handle. And we're using it to draw the curve of the R in the example. So this is just the basic constructor for our draw flight mode. So drawing the R is within our update set point is split into several stages shown in order here. So we have settling at start, we have the left edge, the top edge, the curve, the middle edge, the diagonal, and then when it's done. Essentially what we're doing is we're giving it some maths to be able to draw the lines that it would take and the curves that it would take in order to be able to do the letter R. So as you can see, we have left edge, top edge, we have left edge, top edge where it's going to the top of the R. We've got the curve where it's going. We've got the middle edge. Then we've got that diagonal where it goes out to the bottom right-hand side. So the code to trace the left edge just sets the target position and publishes the message. So we have whatever the target position is. So we've got a little bit of maths here saying where we need to go. The position reach function checks if we're within a certain threshold from the target and moving at a slow speed. So then when it's finished, it knows that it needs to be able to go on to the next state. So if we go back to where we were before, so it's when the left edge is finished, it's going to go onto the top edge, etc., etc. Okay, so now we've seen how to create a custom flight mode. Let's see how to create a flight mode executor to run through the sequence of flight modes. An executor needs an owned mode. So this is a flight mode that triggers the executor. So when this mode is selected, the executor is active and has the ability to switch to other modes. So in this example, our custom flight mode, which is what we installed at the start, is the executor's own mode. And in the constructor, we configure the custom flight mode to activate as soon as the ROS node is loaded. And then basically it's going to go to settling, and then it's going to go to left and to top and to the curve. I did this earlier on because QGC was misbehaving. So once the executor activates, we move to our business logic in run state. which is here. So we have draw mode executor. It's owned mode, as you can see here. It's going to activate immediately in this example. And then it's going to go to run state. And when it's finished with run state with success, it's going to go on whatever the next part of the run state is. So built-in flight modes can be activated as functions. We have arm and takeoff. You pass them a callback when they call, and so when they finish or when something goes wrong, that they can respond. And then we also use this to move on to the next mode, which is why it's important to call completed at the end of each custom flight mode so that it knows that it needs to go on the next state. So within run state, we have arming, taking off, draw mode, return to land, and then wait until disarmed. Okay.
Hey, Godfrey, we got a quick question. It's
Sure.
Can you use Python instead?
Yes, you can. I've got the next one is actually going to be Python. And what I really need to do is I want to make sure that I get this again so I can show you with it where we ended up. So hopefully this will run this time. Okay. Yeah. Okay. Let's go. So what it's doing now is it's going through the different states. So it's doing the left edge. You can see on the left side of the screen, we have Gazebo running, which is our simulator. On the right-hand screen, we have Q ground control. It's just on the left edge. It's doing the top edge. It's doing the curve now to come back to the center. And then it's going to do the R. So it's going down to the bottom right, which are each of the different states that we determined. And then because it has to come home, it's just going to give us close the loop. There we go. Okay, if you want to see the code is here. So we have our update set point. This is the states that I was talking about. So we have the different state for the curve. We have the one for the middle edge. So basically, it's just a little bit of maths to get what we need to do. But the reason why I like this so much is because my code is contained in, there's really not much going on here, and it's just contained in one file. So whatever logic is really nicely compartmentalized, which means I don't have to do it in by changing the firmware, which also causes other issues because if I'm running a firmware, is that compatible with other people's firmware? What happens if the PX4 firmware gets updated? Does that mean that I'm not going to be updated, or do I have to rewrite my code for whatever changed? So just the whole fact of ROS2 being just so easy to hook into different nodes, I think it's going to be a pretty much of a game changer. And I do hate that term, but I think this one is definitely going to have legs.
Godfrey, we got two questions. Can we control multiple drones through it?
Yes, because there is a streaming thing that we can do too as well. So swarms lend themselves very well to ROS2, and that might actually be a good topic for a future talk.
So the other question is how about an indoor test? I want to use Vicon localization, not GPS. IMU fusion from PXOC 6X or 6C. So you should be able to do that.
You should be able to do that. I don't know off the top of my head, but I would imagine that if you could well, you could do a bunch of things. So PX4 will support virtual sticks. So you can get your node to pass in the information across the bridge to the same as what we did with our set points to make it go to using the virtual sticks to fly to in a direction at a certain speed till it gets to whatever XY coordinates that you pointed at. So yes, I would imagine that this would definitely lend itself to that use case. Okay, second one that I wanted to talk about, I really didn't have much to do with it at all. So this comes from this GitHub repo, and I haven't gone into this into too much detail, but I wanted to show it because it's a Python example, and we've already had a couple of people ask about Python, so it's a good way of seeing how everything fits together. So it's a more complex example. But it's a really good demo to see what's possible with PX4 and ROS2. So I wanted to kind of add this at the end. So what do we have? So we download the Docker image and run the simulation. as with always, I always run things locally, so there's no reason we couldn't locally. And I just want to show you what it looks like. So I'm going to have to get out of this for a second. Here's the repo, which is in the resources. It's a really short video, but you should be able to see how it's all put together. And then we're going to talk a little bit about the code. So you can see very quickly he ran through what I was doing here. So this is the raceway model that's set up, and then we have, is it stopped? Stopped. What it should be doing is doing object detection. I don't know why it's doing this tonight. Wait a second. More than one way to skin a cat. Okay, so he's running two things. There's the camera bridge, and there's also a key bridge, keyboard bridge. The frames are being chopped so that they're being passed to YOLOv8, and then YOLOv8 is doing some object detection. Yeah, I don't know what's happening with my internet today. Okay, and then it just lands again. So let's get out of that real quick.
Okay, we got two more questions.
Sure.
How do you do obstacle avoidance using PX4 firmware instead of autopilot? That might be too big a scope to handle right here, but maybe point the person in the right direction.
Yeah, but can we do it later? Because it's
Yeah.
not really. Yeah, we can follow up with that later on if that's okay.
Yep, no problem. And then the
Okay,
second. Okay.
sure.
Do you want the other one?
Yes, please.
Do you know if ROS2 is sending twist movement messages through DDS to PX4's messaging platform? So yeah, it should be translating to DDS because that's the new standard for ROS2, right?
Yep, that's what it's using.
Okay.
Okay. All right, so so on the left we have the Gazebo simulation. So in the background is the camera's view with object detection. And in the bottom right, so this is a black window. You can control the drone with your keyboard. So it's kind of like the WASD, which you see all the time with everything from drone as first responders to just gaming platforms without a joystick. Okay, so to get this to run, we need to create the micro XRC agent. You probably saw when I ran it real quick that it was in the background. Start custom Gazebo PX4 simulation. This was a little bit harder to get running because it's using, same as what I was using. It's using the garden one, which is the earlier version. So Gazebo Garden, which is kind of end of life. But there's no reason, but it's working, so that's fine. So start a custom Gazebo PX4 simulation, run the ROS2 image bridge camera, and then run two custom Python scripts for the object detection and the keyboard control. Okay. So then Gazebo can load pre-made worlds, so that's why we were looking at the car simulation here. The simulated drone comes with a functioning depth camera, so you don't need a camera. You just need to make sure that you're running GZ_X500 depth. Let's talk about the ROS and Gazebo integration. So packages exist for integrating Gazebo and ROS. Gazebo is used all the time in ROS2 as well. So basically what you need to do is install the appropriate package, run the setup command for ROS again, get the bridge for the camera and the image, and then we create a ROS node, and then the ROS node reads the frames from the simulated camera in Gazebo and publishes them to the ROS topic called camera. And then we have two Python files, the UAV camera detection, that creates a ROS node to subscribe to the camera topic. And then it runs, so basically what it does is it's going to take the frames and then run object detection using YOLOv8 model, and then displays the result, which is the yellow boundaries with the percentage confidence of what it was looking at. And then the second thing that we have is the keyboard mav SDK test. So this uses Pygame. Pygame is a library that people use. We talked about it earlier when we were doing some of the sorry, it was on a different meetup when we were trying to create games for board games using OpenAI. And Pygame is just a Python library that allows you to do keyboard inputs, capture keyboard inputs. And then we can send that to mavlink commands to move the drone using the mav SDK. So you don't really have to use mavlink. You could use ROS if you wanted to, but certainly this is an example which is using mavlink, so it's another good way of saying, you don't have to be all in on ROS. You can use what you already know and then just use ROS as a bridge for whatever sensors that you want to connect to. Okay, and all of those are in the resources. So we have the following resources. So it's the user guide. We have information on the PX4 ROS2 interface library. And then the two pieces of code, the first example that I showed you, which is the PX4 ROS2 flight mode, and then the Monomati, which was the Gazebo one. Each of those are here. So this is the Gazebo. Basically, everything happens within the UAV camera detection and then the keyboard mav SDK. For the C++ example, if you want to look at the one that I borrowed from Auterion with some slight changes. And then we have the ROS2 user guide, which is a lot of what I talked about today. I stole a lot of the images from there too as well. And then the ROS2 interface library, if you want to learn more about that too as well, and how to build a workspace. So it's, if you can't follow my instructions or the video, this is a great place to go back to see somebody who's put a lot more care and attention into getting this working. Okay, and then I did want to say that next month we are going to build our own remote controller. So we'll be basically taking a bunch of a high nits screen that we got off AliExpress, some 3D printed parts. We started off with Steam Deck, had its STL file. So we started off with that to try and use that as the basis for our controller, but I think we've moved on to something else now. So next month in April, probably the second week in April, we'll talk about how to put that together, and interested in your feedback too again, and then we'll probably go back to ROS2 after that. So before I finish up, have we got any final questions?
Before we do final questions, we do have some. I just want to remind people we have the Philadelphia meetup coming up, and you'll be speaking at that. So if you want to get in front of Godfrey in person, you could come to the meetup, which is next week on March 26th at University of Pennsylvania. The sign up for that is right here. Oh, there you go. And now I'll bring up the questions. Let's see. So as you're working in simulation, can we use the same code for a real drone, or do we need to modify the code? If yes, what modifications are required?
There won't be any modifications. You're just running it. It's the same way as you do simulations. So you're going to run a simulator for you start off with software in the loop, so you just run it without your orange cube or whatever you're using for PX4, and then you run it with your orange cube hardware in the loop, and then you run it on the drone. So that's it.
Object tracking flight mode would be a cool follow-up to this demo.
I think that's a good idea. Yep, I'll take note of that.
Xeno Robotics over on YouTube. I wrote my own obstacle avoidance algorithm from LiDAR readings in a Python PX4 script. So a little humble brag there. Is there any way, this is from Piyush, is there any way I can consult with you, Godfrey?
Sure.
Yeah, just reach out. Here or Meetup or LinkedIn. Can we do the same example with Autopilot? Do they have a ROS2 library?
I do not know.
I will check into that for you, Faiz, and if there is information on that, I'll put it in the meetup, and maybe in the YouTube comments. What's the range of ROS messages can reach up to? That would depend on the hardware, right? The radio.
I don't understand the question.
Yeah, I think they're worried about distance. Range of ROS messages can reach up to, not range of how many. It's how far, I would assume. Malik, if you want to provide extra information, we could follow up on that question. What is the difference between Mavlink and ROS for controlling PX4, and can I use ROS Noetic with this?
Is that the version of ROS that you're talking about?
Yes.
It looks like it's only two versions that they have. I think I showed it in one of the slides.
Okay, no problem. Intel
Hold
Real,
on, I'll get there.
yeah, you get it? Okay. Yeah, we
It's
got
Foxy and Humble is what I'm saying.
that might change, or they might update that soon with the next release of PX4.
That's all I'm saying in the documentation.
Yeah. In production, would you have the, this is from Intel RealSense over on YouTube. In production, would you have the Ubuntu and ROS2 running on the robot, or could the drone communicate with your ROS2 environment on the ground?
I'd imagine this is running off a companion computer, so I'd say it'd be on a drone.
Intrepid AI, this is very interesting. Let's stay in touch. Um, are you using a Jetson Nano as your companion computer, or do you
Yeah,
have any yeah? Not a,
yeah, Jetson Nano or Jetson Orin.
Yeah, Jetson Nano or Aura Nano or Xavier XV, I think, and Voxel 2 is also a favorite out there for companion computers.
Okay, so the range of ROS messages, but if you're running it from a companion computer, then there is no problem with range. But yeah, I'm imagining this is running on a companion computer.
So, hello, thank you very much for sharing these demos. Could you work on a Raspberry Pi 5 with Ubuntu 24.04? You can. I would not recommend that personally. It's not built to task, and you're not going to get a lot of flight time because of the way that that thing consumes power, and also heat is a consideration there. Yeah, I'm putting together a big white paper on companion computer, so I know everything about him right now. What
I'm glad
ROS?
you could answer that one.
That was a little esoteric. What ROS and ROS2 versions are supported? So I think it's only ROS2.
It's ROS2, Humble, and Foxy is what I'm saying in the install.
Yeah, I don't think this is supported with ROS1, probably because of the messaging.
Yeah,
Um,
because one's centralized and one's decentralized, so it won't work with ROS1.
uh, will the recording of this video be available? Yes, you could find it here on the chat, and you could also find it on the the meetup group. It's in the comments there. I put it earlier. Let's see. Zeno Robotics also said he's used a Raspberry Pi 4. Vision is a problem though, so extra information from the YouTube chat. Can we create a survey grid using just 4 VIO-based coordinates using ROS2 interface?
No, off the top of my head, I do not know the answer. Sorry. I can look into it.
I think we hit all of them.
Cool. And we're under our 5 minutes, so that's cool. Well, thank you, everybody. That was fun.
Yeah, that was a good one. Thank you again.
Uh,